Good morning and welcome to MAE 209, Probability and Statistics. My name is Richard Kohar and this is Lecture 16, the Cumulative Distribution Function and Expected Value of a Continuous Random Variable. It's good to see everyone there. We just finished Quiz 2. And I'll make a note to speak with the person that was talking about the grace period. Okay. So in the last section we covered section 4.1, and in this one we'll be covering 4.2 in the textbook. Yes. So the two people that are just in the just send me an email so I remember. Okay. So for our warm-up exercise, what we're going to do is we're going to just refresh ourselves what we were talking about last time. And we were talking from 4.1, we were talking about probability density functions. And let's just kind of review what a probability density function was. So we suppose that we have a random variable x is continuous. Whose probability density function is so here we're going to use k times x squared, and this is defined for the values between 1 and 2. And if it's outside of this range, it'll be 0 otherwise. So the first question that we can ask what is the value of k? So what it's asking about is basically we need to make sure that this PDF, this probability density function, satisfies those two conditions that we had previously that we'd mentioned. So those two conditions were that the probability density function has to be non-negative for all values of x, and that if you integrate it over the entire real line, that it should be 1. So what I can tell you is that x squared, that's a parabola, and as long as this k value here is positive, this will also be opening upwards. Again, that's for ax squared. That's where a is positive. And if it's negative, then it would be the other way. So yes, as long as k is going to be positive, this should be also this will be at least non-negative. And the other thing that we need to check then is to make sure that when we integrate over the entire reals, that it's equal to 1. So what we need to check is that from 1 to 2, that f of x dx is equal to 1. And just substituting that in, we have kx squared dx is equal to 1. We can bring the k out because it is a constant. It doesn't depend on x, so that's okay what I'm doing right here. I can bring the k over to the right-hand side. And integrating that, I get 1/3 x cubed, and we need to integrate that from 1 to 2 of 1 over x. So that should be 8/3 minus 1/3. So that should be our value for k. So for those that are just tuning or listening or tuning in, is that straightforward enough? Yep. Okay, good. So then when you have things like that, so therefore the PDF is three sevenths x squared from 1 to 2 and 0 otherwise. Okay, perfect. And then from there, you can answer questions like, so if we make this say part A, up here we'll do part B. Then we'll do say something like the probability that x is greater than let's say 3/2. So in this case, we'll be integrating from 1 to 3/2 of 3/7 x squared dx So again, I can factor that out. I have the 3/7 out each side. And then I will have 1/3 x cubed, and I'm integrating from 1 to 3/2. And in the chat, what should that give us? Okay, so I'm getting, oh, did I make a mistake? 3/7? Okay, what's everyone else getting then? Oh, okay. So what I'm getting is 37 over 56, which if I do a decimal approximation should be, okay, yes. Okay. So this is our warm-up exercise. Again, here's the PDF that we were working with. We were making sure that the PDF satisfies those two conditions, that it's positive, well, that it's non-negative, and that it sums to 1 or integrates to 1. And so that's, you can think of, this is what will help us ensure that if we integrate over this parabola, so again, if we're integrating from that, that area is 1. Okay, so we were talking about probability density functions, but something like this should be familiar. From our discrete random variables, what type of function is this describing here now? What I've circled here in like this blue-green, the CDF, yes. And just like the CDF from when we were doing the discrete random variables, it's all the probabilities up to and including the point that we're looking at. So and again, someone was asking me last time, why are we using the CDF? Why is it useful? And I said, you know, I will defer it to when we get to more talks about continuous random variables. I think of it much more useful in the continuous random variable setting because we can't calculate the probability of individual points. So, you know, working with a PD a PMF in the discrete random variable case is very straightforward. We can sum them up, and but when we work with continuous random variables, again, we can't come up with a probability that's greater than 0 when we integrate on a point. So we have to have some interval that we're integrating over. So that's where we usually come into play with CDFs. Okay, so that's a good lead-in to what we're doing, which is the CDF. Okay. So here comes a definition. So the cumulative distribution function, and that's again what we're calling the CDF. And so when we're talking about PDFs, we're talking with little f. And when we're talking about CDFs, we'll use the big capital F. Of a continuous random variable x, a capital X here, is defined for every number little x by, so again we're using capital F, the other notation that we can use is that that the random variable is less than or equal to some value. And to get that, we start from negative infinity up to x, because that's our limits of integration. So we're starting all from the farthest far of left and going up to a certain point. Oh, maybe it might be helpful as we're doing this. So right here, this would be called our f of x. Here's our x, and we'll say at this point right here is our x, and this is what we want. That's the area. So we want all that area up to x. So we'll use f of, and we need our d for our integral. Now, again, I've already been using x in this case, so I can't use this inside of here. I need a dummy variable, so that's why I'll write y here. So that is the cumulative distribution function. For a continuous random variable. Now, to calculate other probabilities, if we wanted to calculate, say, the probability that x is greater than some value, let's say a, well, what I would use is my complement rule. I would take 1 minus the probability that x is less than or equal to a, which then means that it's 1 minus f at a. So again, this is looking at it from the right-hand side. So really what we're doing in that case, let me just kind of draw. Let's say that's our point A. Well, then what we want is the area to the right of it. So that is right over here is what I would call, oops, and there's this kind of the area that we can calculate is this over here. And what this is calculating over here is that complement. So over here, and the second part, if I'm working between two values, say A and B, I'm trying to draw the same function every time, so again, sketching it. And that is actually distribution. It's the normal distribution, but again, we're going to see that in next class. So in this case, what we want is from, say, A to B, and the area we want in here so the way that we can do that is that if you want the two areas and we need to use the CDF, or that we know what the CDF is, what we need to do is calculate all the area up to B. So here's B, and so be all this area here. So you would take all the area up to that point. And then if I have this point up here, this is A, we want to subtract that. So that's all that area to here. So again, when I remove this part right here, then all what I'm left with is that area that I wanted. Okay, and what I can do then is kind of rewrite that using our CDF. So again, that the probability between those two values of A and B is equal to the cumulative density function, or sorry, the cumulative distribution function up to B. And then we remove the area we don't want up to A. Okay. Is there any questions about that so far? Okay, so then so here's an example that we'll do. Find the CDF, or the cumulative distribution function, of the uniform distribution. So we'll say let X be a uniform random variable on the interval from, let's say, A to B. Okay, then the PDF should have the form of one over B minus A, and that's if it's between those values of A and B, and 0 otherwise. Is everyone okay so far with that? So again, what you have to remember so we have some point A and B, and that's our function. That's the f of x. Okay, so then all we have to do is just use the definition of what we had for a CDF. So we're integrating from minus infinity up to x. So we have f of x. So now notice that this is the capital F. So that's the CDF. So we're integrating from minus infinity to x. I need to use my dummy variable of y. Now, if you notice, if we go from minus infinity, there's 0 up until a. So we don't actually have to worry about when it's less than a. So what I need to do is actually break this into 3 cases. So there's kind of 3 cases right here. There's kind of a case right there, case 1, and that's where there's no probability that's being accumulated. We have the second part right here where we're integrating along that PDF, and then after here, because it is a PDF, and when you integrate over, you know, the interval that we specified, this should be 1. So we're going from 0, accumulating in the second part, and then by the third part, we should be at 1. So this is really what we're calculating at this point right here, is this second section. So doing this part right here, it will be going from a to x of 1 over b minus a. And then we have dy. Again, 1 over b minus a doesn't depend on y, so I can actually bring that out front of the integral. And you're left with y, where we're integrating from from a to x. And we're almost done. So I have x minus a all over b minus a. So again, we're not quite done yet, because the CDF has to have this final form where we got those 3 cases. So we got to write that out. So here's my third page. So putting this together, so I have, you know, that first section, the second section, and third. So at that point here, that's 0. So that's whenever x is less than a. It'll equal this part, what we calculated for the second region here. And that's when it's between these values. And we'll have 1 when x is greater than b. So if you wanted to plot that, for some arbitrary values of a and b, then it would be 0 up to this point. Then from this point here to say, here's say 1. It linearly increases, and then it goes to 1. Oops. There we go. Okay. Any questions about that so far? Okay. Put that over here. So that's the end of that example. Let's do another one. They said so they say suppose the PDF of x, and in this case they say that, let's say x is the let's say a dynamic load of a bridge in newtons. Newtons is force. Suppose the PDF of x is and they say 1/8 plus 3/8 x. Okay, so this is a linear function. So that means that when we're going to be integrating it, we should be expecting then a quadratic. And 0 otherwise. Okay, thanks again for, I assume that what was in the chat was another more spam. Okay. So, same idea. There'll be 3 parts to that. There'll be the part that's before 0. There'll be the part where we're integrating the 1/8 plus 3/8 x. So that'll be from 0 to 2. And then we'll have the part where it's 1, right? So we'll be, there's kind of a part where it's 0, where we're integrating, and then it'll be 1. So when we're looking at that interval, again, we're using our definition, which again is going from minus infinity to x. So again, we're going to be at 0 otherwise. So like we don't have to worry about everything before 0. So we can just integrate from 0 to 2. So from 0 to x, we'll have 1/8 plus 3/8 x. Oh, and I'm using y. Right. I need to make sure that I use my dummy variable. So you get, when you integrate that, that's 1/8 y plus 3, well, you have 3/8 times 1/2 y squared, going from 0 to x. When you substitute in the 0 for this makes the whole thing 0. So all I have to worry about is substituting in the x. I'm left with 1/8 x plus 3/16 x squared. So again, putting it together, what I get then is, again, it's 0 when it's less than a. (1/8 x plus 3/16). Again, that's when it's from 0 to 2. And then after that part, it'll be 1. So we can do, what is the probability that the dynamic load is between 1 and 1.5 newtons. Instead of a, shouldn't we put 0 when you put Oh, I'm sorry, yes. It should be 0. Thank you. Okay, so thank you for catching that. What we need to do is understand what this is asking. So what is the probability that the dynamic load is between 1 and 1.5? Well, mathematically, in mathematical notation, it should be 1 is less than x, which is less than 1.5. And so what we want is then the probability that x is less than 1.5 minus the probability that x is less than 1 Now again, here it doesn't say if it's inclusive or not. But I am going to slightly abuse some of this notation. And the reason for why I don't have to worry so much about the less than or the less than or equal to is because I'm working with an integral. So I'm going to the limit. And again, it never quite gets to that point. Again, it's a limit. It's approaching it. So when I'm talking about the limit as I'm going to x, I'm getting really close to it, but I don't actually touch it. So I don't actually have to worry too much about this. I can actually use f of 1.5 minus f of 1. So substituting in those values, I get 1/8, 1.5 plus 3/16. Okay. That's for that first part, minus 1/8 plus 3/16. And what does everyone get? Yep. I think that's what I'm getting as well. So I'll put down 4 decimal places. So 2969. Okay. Okay, and the other one is, let's say, what is the probability? That the dynamic load exceeds 1.5. So if we want to calculate that, what it's asking for is the probability that x is greater than 1.5, which is equal to subtracting 1 minus the probability of x less than or equal to 1.5, which is equal to f of 1.5. So it's all of that right here again. I forgot. I have 1/8, 5 plus 3/16, squaring it. So hopefully everyone is matching what I'm getting is 0.3906. Is that what everyone else got? Okay, perfect. So grab another piece of paper. So, just using our fundamental theorem of calculus, you can see what we have. We have, say, a PDF. So this is our probability density function. And that's what we call little f. And over on this side, we'll say the CDF. And so to get from the PDF to the CDF, we integrate So what do you think that we have to do when we want to go from the CDF to the PDF? That's right, we need to differentiate. So as we're coming from this side, what we need to do is take the derivative of it. So we had with the uniform distribution, calculated that it was x minus a over b minus a. And to get to the uniform PDF, we'll need to differentiate. So what we get then is yep, we have to take the derivative. Yep. And again, you have to take the derivative with respect to x. So again, here you have a constant, so we can bring that out. And the derivative of x minus a, well, we just have x here that we need to differentiate because a is a constant, so that goes to 0. And I'm just left with x, so that means that it's just 1. So all I'm left with is 1 over b minus a. Now remember again, this is when that's less than a, between a and b, and when x is greater than b. And the same thing, this is only holding for when it's between a and b. So again, same thing. This is for when it's between a and b, and then otherwise it's 0. Okay. Now in the textbook, they have a different way of talking about percentiles. What I'll do is I'll give an alternative take on this. So percentiles, you can have, people will say like the 25th percentile, the 50th percentile, 75th percentile, 90th percentile. Really what they're looking for is, they're kind of doing the reverse problem. So let's say, let me draw this. We have some curve, or just, well, I should say, let me draw a PDF. Something like that. There's a PDF. And what we'll do is we'll integrate up to a certain point, and we'll call that A. So again, all this all this area below A. Okay, so the problem now is switching from, instead of me specifying what A is, I'm going to specify what the area under the curve is. And the pen's slowly dying. I will specify the area under the curve. Now we know that the total area under the curve should be 1 because, again, this is a PDF. And if I integrate under the entire real line for under the PDF, I should get 1. So this is the problem that we're considering. I will specify the area under the curve. And so let's say I want the 50th percentile, or I want an A where the area under the curve is 0.5. Or you can think of it as 50% of 1. So we have to solve something like this. What the A is where it's equal to 0.5. And that's it. That's what a percentile is. So if you wanted the 95th percentile, you have to solve f of A equals 0.95. Now, why am I so particularly interested about the 50th percentile? What makes it so interesting is that that's the median. So the median, the median of a continuous distribution and they denote it with, in this book, a mu with a little tilde over it. Is the 50th percentile. So that if I write f of of the median, so the little mu with a tilde, that's equal to 0.5. So that means when I write 0.5, this means half of the area under the PDF. Okay. So what that means so there's the median, and so that's kind of a definition. We should probably write that as so definition. So I'm trying to draw that as symmetric as possible. If I have so again, if I have a symmetric distribution, something like this, again, I would have 50% of the area. Well, let's say that I'll call this my line of symmetry. So right here is my line of symmetry, which means that, again, if this is a PDF and it kind of mirrors on both sides, remember when we talked about symmetry with integrals, that basically you can just integrate on one side and just multiply by 2, and that would be what your answer would be. So when you have a symmetric distribution, the line of symmetry at that point is also the median. Half of the area lies to the left of the symmetry line. And half of the area would be on the right. Okay. Let's talk about the expectation now. So when we talk about the expected values, in discrete random variables, when I had x is my random variable, I wanted my expected value. What I would do is I would sum over all the possible values of x. So x times its associated probability. So in this case, we're summing. In the continuous case, we have infinitely many points. So instead, we switch from using a sum to instead we use an integral. Now again, what we'll do is we'll integrate over the entire real line. So we'll say from minus infinity to infinity. And in this case, in the textbook, they may also write it as, instead of writing it as like this notation, they may write it just as a continuous function using kind of just f of x. And also in the textbook, they'll use the expected value, like the e of x, or they may also write mu. And then to just make sure that we're talking about a specific random variable, we could be using more than one, talking about more than one random variables, they'll give a little subscript x. So that's our formula. That's it. And then also as a remark, we can calculate other ones as well. So if you wanted to calculate the expected value of x squared, again, it's going to be from minus infinity to infinity of x squared times its associated probability. And why do I need this? Well, because that same formula that we used for variance with the discrete random variables still holds for this case. So you can use the expected value of x squared minus the expected value squared, and you'll still be able to calculate then your variance. Now with a variance, of course, we had defined it before. As the expected value of x minus mu or you can think of it as from minus infinity to infinity of, so it's our value, x minus mu squared times its associated probability. So 2 ways that you can calculate the variance. So again, variance can be written with the sigma notation. And if you wanted the standard deviation, we can do just sigma is equal to the square root of sigma squared, or you can think of it as just square root of v of x. What is mu in this? Oh, yes. So in the textbook, they're using mu as the expected value. That's a good question. Okay. Is there any questions before we wrap up for today? So would that be a recursive formula in terms of e to the x? Or sorry, e of x. Which formula are you referring to? A recursive formula usually relies on something that you've previously calculated. If you're thinking about this formula right here, no, these are 2 separate things that you have to calculate. One doesn't depend on a previous calculation. So here you would need to calculate this one right here. And then for this one, you calculate this one right here. So there's your formula for this term, and here is your formula for this term, and you have to remember to square it. Oh, and I'll also write out that the way that we write that in math is mu. Just the notation for finding. Oh, no, that's not. No, that's not a recursive formula. Yeah, this is, again, it's a straight integral calculation that you would have to do. At no point do you rely on a previously calculated value for that. Okay. Okay, everyone. Make sure to check out the exercises that have been posted on there. Try out section 4.2 and send me questions if there's problems or issues, or I can't, you're stuck, send me an email. And again, those 2 people that sent me an email comment about the quiz, please send me an email as well, and I'll respond to that. Okay, thank you everyone, and enjoy the rest of your morning.